let me continue where we left yesterday. We discussed Hough transform method yesterday for straight line equation, and today we'll see that we can extend it for other parametric equations as well as some generalized shape also. So for example, if we have to fit data points for a shape like circle, then as long as we can have a parametric equation, for example, for circle with center a comma b and radius r basically, we know the equation of a circle x minus a square plus y minus b square is equal to r square. So now again we'll have some kind of a correspondence between image space and the parameter space. So now in this case, assume there are three parameters: the center x coordinate, center y coordinate, and the radius r. But for now, let us assume radius is known. Let us say we have fixed radius right now. Then we have only two parameters a and b left. Okay, so let us try to understand how the correspondence between a point in an image space will correspond to what in the parameter space. So let us say we have this point. Let us say we have this point in the image space, and we know the radius is r. Radius of this circle is, let us say, known to be r, some value. So this point will correspond to what kind of a shape in parameter space? Anybody has any idea? So this is known, let us say this point is known x0 comma y0. Then for this point, what will be the location, what all points will cover in a parameter space? Just if you remember, in straight line, for straight line, a point in an image space corresponded to a line in the Hough space, whereas a line in a Hough space corresponded to the point in a image space. So if you can recollect that correspondence, so something similar will happen here also. So if so let me just continue here. If anybody wants to answer, you can answer, otherwise I'll continue. So let us say we know x0 and y0 is fixed for a particular point. Then how this equation looks like? It is again an equation of a circle with the center as x0 comma y0. Somebody is not mute, it seems. So if you take this, if you can rewrite this equation as a minus x0 square plus b minus y0 square is equal to r square. So again, this is in AB space. This is again an equation of a circle with this point as center as x0 comma y0, as a as x0, b as y0, and again the radius, same radius r. So it will correspond to a circle with radius r and the center x0 comma y0. I hope everybody can appreciate that. And if we take another point will correspond to another circle with that as a center and the same radius r. And if we take another point, that will also correspond to another circle with that as a center and radius r. So now basically, what is the point here now? So how will you know which is the circle in the image space? Because r is known, what we need to know the center xc comma yc, let us say. We want to know this center. How we will know this center point? What in the image, in the Hough space, will correspond to this center location in the image space? Anybody? Are you following, or
so the intersection point?
Yes, good. So the intersection point here, just like in the earlier case also, multiple lines wherever they meet intersect, that will be That will be the equation for the actual x0 y0 in this case. So similarly here, all these equations where they intersect, basically that will be your correspond to your center in the for the center in the image space. So, and that will also, if you see this as a, if you construct this space as an accumulator array, and for all these points you cast a vote, so which location will get the maximum vote? Which is this location, because most of the circles that will correspond that will be basically for each point on this circle, they will all intersect at this point. So you are going to get the maximum vote for this location, and that will give you the center location. So I hope you can understand. So something similar can be done. Same thing that we did for straight line equation, we can do the same algorithm we'll use. For each edge point, we will cast a vote. We'll basically divide into a accumulator bin, and we will basically count a vote, and that will give us the actual center. But the problem is radius is not known. In general, if radius is known, that may happen for some cases. We'll show an exact application. For example, here, let us say we were trying to detect these coins in this image, and these coins are known coins. They are pennies and quarters. They are US coins. So the radius of these is known pre-hand mostly. So it is not difficult to know the radius. So radius is known. There are two types of circles. One is your penny, and another is your quarters. So they have two different radius. So you can do an edge detection. You will get this kind of an image. Now, if you want to detect the exact circle of the exact location of these coins, you can construct the Hough transform just like that, only with A and B as the axis of the Hough space. And what will happen if you keep the radius, if you use the radius of the penny, then as you see, you will get this kind of a response. And as you can basically see here, the maximum peak is coming at this location, which corresponds to the center of the penny. Whereas for these quarters, you don't get that strong response. So you still get some response. For example, not a focus peak, but you get some kind of a. So what will happen basically, because different pennies can fit into a quarter, so different pennies will basically fit into a quarter. So because the radius of the penny is smaller, so different size pennies can fit into your quarters. So they are going to probably vote for all their locations. So that's why instead of getting one single location, you are getting multiple locations. Although the strength of that vote will not be as peak as this. So you can reject that if you are not interested in that. You will be able to know this is the exact location for the penny. And if you keep the radius for the quarters instead of penny, if you use the radius value as the radius of the quarters, then you can see now we have a strong response at the center of these quarter locations and dim response for the penny. So this will help us to detect the quarter location. So you have to run it 2 times, probably one with radius 1 and another with radius 2, and then combine those detections. You will be able to detect all the circles. So that is one approach. If you know the objects, if they are circled there and if they have different radius, and if you have some estimation of the radius using some prior knowledge, then you can do this way. That is one approach. But in general, radius will not be known. So how will you handle that situation? Then in that case, you have no option but to expand your accumulator space. Your parameter space will not be a 3-dimension now, with radius becoming the 3rd dimension. So you have A and B as usual, but now radius will become the 3rd dimension. So now what will happen to the correspondence? A point in the image space will correspond to what in the Hough space? Any guess, any idea? So now you have to vary radius also. So for some radius, probably this will wait for this much. If you increase the radius, it will vote for this kind of a circle if you further increase. So that is what is going to happen. Earlier one point was just corresponding to one fixed circle for a fixed radius, but now because the radius is changing, so when you have radius small, probably this point is going to, so A and B will be somewhere here, and for smaller radius it is going to basically vote for a smaller thing, and when radius is large it is going to vote for a larger circle. So if you see, actually it is going to make a kind of a cone kind of a surface. So each point in this will correspond to a cone in this 3D space. So we have here, when we have radius 0, you are just voting for one point. When radius is small, you are waiting for a smaller circle, and when radius is large, you are waiting for a larger circle, and so on. So depending on what is the limit that you set for radius, you will vote for all those locations in a cone kind of a pattern. So, and then another point will vote for another cone, and so on. And again, then you will have intersection somewhere where all these cones will intersect, and they will finally lead to one unique circle and radius value. Sorry, what is happening? My eraser is not working. Anyhow, so I hope you can understand something similar will happen analogously. So now these cones will intersect, two cones will probably intersect in a kind of a circle, and then multiple cones will intersect finally to a point. That point will uniquely define the A, B and R value, and that will uniquely define the center of this circle and the radius of this circle. But the problem is now, when you do it for a three-dimensional space, not only your space complexity increases, but again your accuracy will suffer a little bit, because as we said, as you increase one, as your feature points become multi-dimensional, then the accuracy basically suffers a little bit. So you will have to do it little bit carefully. So some approach, what they do is, if radius is unknown, they use gradient information, just like we did for straight line equation also. If gradient is known, then we can avoid one loop inside. We don't have to change the theta value, because gradient for fixed line, the gradient will be fixed. So we don't have to basically vary the gradient. So similarly here also we can do something similar. Radius may not be known, but gradient is known, because at this point your gradient will be in this direction, and your gradient direction will basically be in some direction. So now if you have to move, you have to come to a center, you have to move all along this line only. So you have to vary your radius along this line only, instead of varying radius arbitrarily. So if gradient information is known, then to know your center location for this, you have to just traverse this direction. So you have to vary your R only in this direction. So in that case, in Hough space, you will end up in just one line. So you will vote along these directions where radius is increasing in this direction is variable. So if for different radius, you will cast vote differently. Your center is going to lie along this direction. So in this case, your center will lie along this line. Only in one direction it will lie, rather than on the entire cone, because gradient information is known. So using that, you will basically you will end up voting only in one particular direction. So that will simplify your things, because now basically although you have three dimension, but the number of votes that will be casted will be less. So the chances of accuracy will improve, and that is what most people end up doing if you have to do circle detection basically. So then something similar as we did for straight line equation. For every h pixel, we'll cast a vote. I think the pen is okay. So for every h pixel, not a pen. Pen is not working. Anyhow, so I'll just, yeah, now it started. I think the system is getting slow. So for every edge pixel, basically we'll cast a vote, and how we'll cast vote, we don't know R value, so R we have to vary from some minimum and some maximum value based on your estimation of your image, and then we will because we anyhow we have calculated the edge point, so we know the gradient direction along that edge point. So we'll use that gradient direction. Again we'll use, so again instead of using the similar the normal equation of circle, we'll use again go for a polar representation because we want to utilize this theta value. So again you can see how you can use this polar representation for a circle. X will be equal to a plus r cos theta, y will be equal to b plus r sin theta. So that is the equation of circle in a polar representation with theta, the angle that it makes from the center. So you will use that one. So we know the theta, we know the r, then we can calculate a and b, and we are going to vote for that a, b and r. We'll increment the count. So we'll do it for r from r minimum to r maximum, but they are only going to vote in one particular direction because theta is fixed. So it will end up less number instead of some. It will be more easy. It will be more easier to localize your peak location rather than in the normal way if you have to go for a three-dimensional thing. I'm sorry, my system is hanging, so I don't have to. I think I'll have to stop using pen. So some practical tips how before you use your Hough transform. We should minimize irrelevant tokens first. So we can take edge points with significant gradient magnitude instead of using all edge points. We can cast votes for those only which have good enough gradient magnitude. So we will now utilize the gradient magnitude also. So that will avoid random noise locations to vote to make their vote, because their gradient probably will be less. Another thing is we have to use a good discretization. So how fine you make your bins, because if you make your bins too coarse, means if you take a larger steps, how you discretize in a larger interval, then what will happen? Large votes obtain when too many different lines corresponds to a single bucket. So what will happen, because now many more lines will fall into just one single bin. So instead of precise one line, you may have a line with different theta, smaller thetas. They all will basically vote for they will all correspond to just one bin. So that way you'll be able to not able to precisely locate your the bin your straight line equation. It will be little bit accuracy will be compromised. If you make it too fine, then there is also a problem, because you may miss some lines, because some points which are not exactly falling on that line. So let us say we are interested in detecting this line. Sorry. So let us say your exact location is this, but some points are lying somewhere here, some points are lying somewhere here because of noise. So that may end up doing some problem. So we cannot make it too fine because we have to accumulate all these points also. So little bit trade-off has to be done so that noise do not affect your result, as well as even if you don't have exactly collinear points, still you're able to cast votes for the same bucket. So some trade-off has to be done between making your discretization between too coarse and too fine. So all the either OpenCV function or your Matlab function of Hough transform, that will have these parameters of how fine you want, how much interval you want to increase your theta and your slope, or whatever is the parameter. Another thing is you can also do some kind of smoothing in accumulator array. So as I said many times, we saw instead of one constant peak, you may end up getting some because of making a bin little bit coarse. Instead of one precise or two little bit fine, instead of one precise location, you may get votes in the neighborhood. So sometimes doing a non-maximum separation may displace the location a little bit here and there. So you can do first smoothing on the accumulator array itself before picking up the peak points and so on. So some smoothing will take care of little bit, will basically massage the data a little bit so that you don't have you end up getting the peak location in the right bin. And this also we have seen, if you utilize the edge direction, sometimes we are able to reduce the number of parameters by one, or you are able to reduce either one loop or one, you are able to improve your accuracy. So always do that when you are using Hough transform, use the edge directions to improve your result. So these are finally, yeah, if you also want to know which of the points actually voted for that particular straight line or circle, you can keep tags on the votes. So when you are casting a tag, we can have some linked list information, something which will tell, okay, this vote has been casted from this location of the edge point. So that will help us to identify, okay, which are the points which are exactly voted for this straight line. And that will precisely help you draw the exact line on the image if you want to do that. So you can use tagging also on the votes, which who is voting for where. Basically, you can use that information to know that. So these are some practical tips in the when you in the OpenCV function. If you use some library functions, you will have they will give parameters to adjust these to whether you use edge direction or do all that, and that you can play around with this. I have a Matlab Demo to show you, but unfortunately, it's a tablet that I'm using. I cannot install Matlab here because it makes the system very slow. So I have it in another system, so I cannot show you a demo here. Probably I'll record it and later on share it. And the basic purpose of the demo was just to show this, how changing these parameters your results changes. So it was a good demo, but today I cannot show it. Later on we'll show it if time permits. So any question here? I will conclude the pros and cons of Hough transform in the next lecture, which we have for which I have a recording. So I'll just play the recording. But before playing the recording, let us ask if anybody has any question to ask.
Excuse me, sir.
Yes, Gaurav.
Yes, sir. So we can sort of see how powerful Hough transform is for detecting lines and circles. So based on the results that Hough transforms give us, can we say that the usage of an advanced edge detector like Canny is redundant? We can directly work with Sobel and just apply Hough transform to get whatever we wish to.
Not redundant exactly, because Sobel itself will not give the will give many points, and you will have to, as you have seen. So Canny is going to basically refine those edge locations. So Canny is also doing a lot of useful work in terms of minimizing your redundant edge. Sobel is not exactly giving your edge location. It is just giving gradient magnitude for all locations. And simple thresholding does not give you proper things. So Canny is doing something very important work. It is first of all, it is minimizing the number of edge points. So it will help you in applying this Hough transform, because if you have more redundant locations, they will interfere with your results and it will slow your execution also. So Canny, you should do Canny edge detection first, and on that only you should apply Hough. If you simply use Sobel, your result will be a little bit difficult to get the right result. So if you play around with this function, you will see it is not so easy. You have to play around with the parameters also. Even with Canny edge detector, sometimes we will get some redundant lines here and there. So that's why I think demo was useful to show you. But if you are going to use directly Sobel output, probably you will end up it will be even more difficult to get the precise output. So I don't think Canny is a redundant thing. You should use Canny only, and then only you apply this. So later on also we'll see many times, even now we have a more powerful deep learning techniques, but many traditional vision algorithms are still useful. It's not that they have become redundant, because deep learning, these are like black box. Many times they just fail even on a very common sense thing, which a normal traditional algorithm, which has some basic mathematical foundation and some heuristic and some things, that it will be able to easily detect. So still now in computer vision, even though now deep learning techniques are being used, but traditional techniques like all these what we are discussing, they have not become useless. they all have values. Sometimes they are used as pre-processing step, sometimes they are used as post-processing steps, and sometimes they are used just as another method. So later on, your deep learning gives you one prediction or one output, then these traditional methods give you another, and you combine both of them using some kind of a fusion strategy. So that always improves your results. So where if a traditional black box thing does a common sense mistake, probably these will not do those common sense mistakes. And whereas locations of points which are very complicated, which cannot be dealt by this traditional simple heuristic based, but because you have a lot of training data and that is somehow able to handle those things, you get advantage from the deep learning methods. So nothing is it's not redundant. As I what based on my experience I have seen, nothing comes is redundant. Even as simple step as noise reduction, sometimes that also plays a lot of role. So all that we are learning, they all should be experimented when you actually end up applying these techniques. Many of time, even a simple step as smoothing or noise reduction will help you improve the accuracy of your algorithm significantly. I hope my answer it satisfied your answer. But it's good that you asked this question. One more thing I forgot. I have not put it here. This Hough transform is not just limited for shapes for which you have a definite equation which we can write by using a parametric equation. Even a generalized shape like maybe a heart kind of a shape, or maybe a car kind of a shape. You know, car has like in the slides I think I have shown you. My pen is not working today properly. So car may have a particular shape, you know. So if you want to detect like this kind of a shape in the image, even Hough transform, there is a generalized Hough transform for this, slightly different. It is little bit more detailed, so I have just for easiness I have skipped it here. Anybody who is interested, he can read it. It's very easy, it's not much difficult. Only thing is the algorithm is become slightly different. For that we use the generalized template that we have. Let us say we fix the template. If we have a heart shape like thing, we know this is a shape. So using this shape we basically construct a table kind of a thing, where for each point we choose some centroid location, and we choose for each point we see basically what angle it is making with the centroid, and what is the edge direction, and then we create a table basically for each edge direction, what are the points which basically make the same direction, same thing with the center or with the centroid. So we keep a table and then use this table for the test image. In the test image we use the same thing for doing a voting, and then do something so I don't want to again confuse you because it is little bit more detailed. So I just for the sake of I don't want it to make it include it in the syllabus, so I'm not discussing it here, but it is easy to understand, it's not difficult to understand. Only thing is now we use a table. So because now we cannot define this shape by a straightforward equation. To define this shape, we define this shape using a table kind of thing, where we keep the structure of the information of the structure of the shape using the angle that each edge points make with the centroid location and its location and so on. And then that table we use for the testing wherever we have to detect, we use that table information to cast the votes, and that help us to basically detect even a generalized pattern like this. So people have used that also in some papers for doing simple shape which are not very simple. Of course, parabola and other things, kind of things which also can be defined, ellipse, all those can be straight away defined by a parametric equation. They can be very easily applied with a normal Hough transform method. But an irregular shape, not irregular shape, a regular shape, but without a parametric equation, that also can be detected, and people have shown that it works using a generalized Hough transform method.
It could cope with outliers, like if some points were occluded or if some points were noisy. Those can be handled. Not lot of noise. If the points were randomly distributed, then it would not be able to detect. But if the points was within some Gaussian distribution, then we saw some examples where Hough transform was able to fit a good line or any model for shape. and it could also detect multiple instances of, so if there were multiple lines, it was able to detect all of them in a single pass. So we basically generated a Hough accumulator array. So from using the edge points, we voted in the Hough accumulator array. So what was the principle of voting? What was the basic principle of voting which Hough transform used? Why we were saying it was a kind of a voting method? So we saw that a point in an image space corresponded to a line in the Hough space, and so for every edge point in the image space, we voted for multiple different lines in the Hough space. The line which got the maximum vote means came from the maximum edge points. The maximum edge points which if those edge points actually lied on a single line, then all of those edge points will consistently vote for one single line, or at least multiple specific lines, not random lines. And whereas those were outliers or those were other things, they would vote for some random lines. So the actual line which was there, actually the best the actual good line which would fit on those edge points would get the maximum vote. So that was the basic idea of voting method, that the voting principle that was underlying the Hough transform method. But the problem with Hough transform was that we needed to basically generate an accumulator array. So for a single line, we just needed a two-dimensional matrix, a 2D matrix. For circle, we needed actually a three-dimensional space, A, B, and the radius R, and so on. So the problem was the complexity of this Hough space, and then the search within that Hough space will increase exponentially with the number of model parameters. So as the model parameters increased, the voting procedure will become more and more difficult. Not only the memory requirement, but the problem is now to search within those Hough space, the bins which are peak values will get little problematic. And even some noise, some non-target shapes which may not be, for example, line, but just almost approximating to a line, they can also produce some spurious peaks. So finding a distinct peak was bit difficult, in the sense we have to adjust the parameters. So for example, we had to adjust the bin size. If you go for too fine a bin, there was some problem. If we make our bins too coarse, it was a problem. So we had to adjust the good grid size in order to find the good peaks. So these were some problems with the Hough transform. So we'll try to see today a technique which possibly takes care of these disadvantages, which performs much better uh, in terms of these problems.